Right. Well, thank you very much, Jacob, for inviting me. I'm thrilled to be talking for the Harvard Foundation seminars, and I'll get going. So this is joint work with Ronnie Hermens and Gijs Leegwater. And some of you may have heard a version of this, but this is probably the first time that we'll have really plenty of time for discussion of this. Right. So that's that's what I'm going to say. I'll start with stuff that's fairly well known to everyone. Bell's theorem, and then some subtleties. And then go on to discuss what we might really mean by signaling in principle, and then setting up the conditions under which one might be able to use measurement, the violation of measurement independence to signal in principle. And then we'll tie it in with Bell's theorem, when violations of Bell's theorem might in fact suggest that we've got violations of measurement independence, and then go on and discuss the implications of the results. So let's start with what we all know and love. Sort of standard Bell setup. We've got a maximal entangled state. Alice and Bob measure on the two sides, and I prime, JJ prime denote their measurement contexts. I will be some measurement context appropriate to measure A, and so on and so forth. But they may include extra details, but they are the measurement context for measuring certain observables. Now, when we want to derive the Bell inequalities, we standardly assume conditions that Shimony has called outcome independence and parameter independence. The probabilities or the expectation values of A and B factorize, and then these factors are sort of independent of the measurement context on the other side, and that using standard manipulations gives us certain kind of expression, which is always between -2 and +2, and then a little averaging gives us the Bell inequalities. But in order to get an average that's also between -2 and 2, we need to make an extra assumption, which is not always mentioned explicitly. We need to assume that the distribution of the hidden variables is in fact the same whichever experiment we are doing, independently of which settings Alice and Bob have chosen. And this goes under various kinds of names. We are using the name measurement independence for it. And it's needed because if in each experiment we might have a different distribution of the hidden variables, then we get separate averages in each of the four terms down here. And so the averaged expression is going to be between -4 and +4, and we can violate the Bell inequalities. And just a small remark, measurement independence is often treated in the literature by considering the settings as random variables, and then looking at correlations between the settings and the hidden variables. I won't be using that approach. I'll always treat the settings as parameters, and the distribution of the hidden variables will be indexed by these parameters. Okay, so the interest in violations of measurement independence is that they might lead to local explanations of the violations of the Bell inequalities, because the Bell inequalities might be violated if measurement independence is violated, while satisfying both outcome independence and parameter independence. Now, famously, Bell thought this way out of Bell's theorem was conspiratorial. I'll put up here. I mean, this picture here, which looks like it comes out of Doctor Who. That's one of the famous Swiss lotto machines. Bell had this favorite example. What if we let the settings on Alice's and Bob's side be chosen by Swiss lottery machines? How could the Swiss lottery, the outcomes of the Swiss lottery machines, be correlated with the hidden variables? That would be some kind of conspiracy. And indeed, if we imagine, that there's some common cause, that leads to certain distribution of hidden variables and certain outcomes of the Swiss lottery machines, that would be very weird. We've got some kind of contingent common cause, that then leads to these weird correlations. That's not the kind of thing we like or expect or anything. However, that's not the only way that we can think of violations of measurement independence. And two authors in particular, Hugh Price and Gerard Toft, have been advocating for ways of thinking that we might get violations of measurement independence, that are much more plausible. So the idea is that we might have some direct retrocausal links. Some direct retrocausal links from the settings to the hidden variables. So some direct influence that propagates backwards in time. So that's slightly unusual, but why not? If it gives us locality. Some direct influence propagating backwards in time from the settings, which are thus free variables, but influence the distribution of the hidden variables. And that's Hugh Price's idea. Or there might be some kind of sort of global constraints which sort of enforce, at all times, certain kinds of dependencies, which maybe we should think of as acausal, but maybe it doesn't make much sense to make any finer distinctions. In either case, and this is what we want to focus on. There's going to be some kind of robust dependence of the hidden variables on the settings. So changing the settings is going to change the distribution of hidden variables. That's going to be the way of violating measurement independence, that we want to focus on in this talk. And so, if you don't like retrocausation, if you don't like these global constraints, you'll be less interested in what I have to say. But hopefully, what I've got to say will be interesting enough that you might you might consider ritual causation or global constraints. So now, if that's our setting, there is an obvious question to ask. Could we have signaling from Alice to Bob, which proceeds not via space-like influences, like in the Bohm theory, for instance, but in a zigzag. So we've got time-like or light-like influence back from Alice's settings to the hidden variables, and then sort of standard causation. Hidden variables are the particles move to the to the other detector, carrying the hidden variables with them, and producing a result. But we get a sort of zigzag causal influence from Alice's settings to Bob's outcome. And indeed, could there be ways of using such a mechanism to signal from Alice to Bob? And the answer is going to be yes. We're going to sort of spell out conditions under which this this would be possible, at least in principle. And well, it may sound obvious because if we've got influences backwards in time and forwards in time, then yes, it should be possible to sort of to signal in a zigzag, but this is but actually it's not going to be quite as trivial, because there are going to be certain kinds of constraints. It's not that we can do whatever we want with hidden variables. It's never the case with hidden variables theories. In the Bohm theory, we know there are all kinds of limitations on what we may or may not do, and we need to think about what kinds of conditions might be realized so that we can do unusual things. The same kind of thing is going to happen here. So let's get going. First of all, we should think rather carefully about what we're aiming for. We want to establish conditions under which one might be able to signal in principle using violations of measurement independence. But what do we mean by signaling in principle? And I'll use the example of the Bohm theory. Bohm theory, pilot wave theory, that's a theory in which we have a beautiful example of action at a distance, and here in the in the case of the EPR setup, what happens is that depending on where on whether it is at the North Pole or South Pole on Alice's side that her magnetic field is stronger, depending on that, Bob's particle will follow one trajectory or another. So these are things that Alice can control. She can choose whether the polarity of the so she's got two variables that she can control: the polarity of the field and the gradient of the field. And depending on how those two variables relate to each other, Bob's particle will follow one trajectory or another. So that's action at a distance. Clearly, we've got a mechanism in the dynamics, but can it be used to signal in principle? And often one says, oh yes, obviously, in principle, Alice could signal, because if she knew what the initial position of her particle is, then by choosing the details of experimental arrangement, she can determine which way her particle goes, and therefore ensure that Bob's particle goes the way that corresponds to the opposite outcome. But knowing the positions, knowing the hidden variables is tricky. So we shouldn't be naive about it. So, what do we mean by knowing the hidden variables, knowing that Alice knows the position of her particle? We could mean one of two things. One is Alice might be what's often called a subquantum demon. So some being a bit like Maxwell's demon, who is able to know things that physical beings are not able to know, or able to control things that physical beings are not able to control. So in this case, Alice would just be able to see her particle's position without interacting with it quantum mechanically. And sure, if she was able to do that, then she could signal. But that's impossible. I mean, even calling this in principle is a bit disingenuous. Yes, only a demon could do that, not a physical being. If Alice is a physical being, in order to know to a certain degree of precision, what the position of her particle is, she has to quantum mechanically interact with her particle, and she gets entangled with her particle, and that changes the pilot wave that, in fact, guides her particle, and so the situation is different now. So this is not the intuition that we should follow. There's a second intuition. Alice might have a disequilibrium ensemble. So she might have an ensemble of particles that are distributed not according to mod psi squared. Even though she prepared, or even though the state is a singlet state, it could be. Sorry, it's not a. It's not a spin that's important here. Even though the position distribution, according to the quantum state, would be uniform, in the top half, between top half and bottom half of the experimental arrangement. It so happens that all the particles are in the top half. If Alice knows that, then she can again use that information to signal, to make sure that on Bob's side, Bob always gets one particular result, or gets whatever result she wants. And now, if this was just a statistical fluke, then maybe it isn't really signaling either. By a statistical fluke, we can all signal, using EPR pairs. If we are lucky, we try and send a message across, and if we are very, very lucky, what Bob sees on the other side will correspond to our message. By a statistical fluke, that's not really signaling. What we mean is there might be some reliable source of disequilibrium that we can find out about experimentally. Now, that's the kind of thing that Anthony Valentini has been proposing for years, trying to find realistic cases where to look for them. formally, using a slightly different language, it would be a case of preparation contextuality. So there are various ways that Charlie could prepare the singlet state, but depending on which experimental arrangement Charlie chooses, even though they always prepare the singlet state, they might prepare different distributions of hidden variables. Well, that will be preparation contextuality, and that's reliably preparing disequilibrium distributions. And along these lines, we can actually think of setting up a signaling protocol. So we would have, here's a particular context K that Charlie uses to prepare the particle pairs, and actually the context includes not just Charlie's settings, but Alice's and Bob's. We've got a violation of measurement independence in our case, and setting up a protocol with these particular choices of experimental arrangements in the three labs. Then we are going to construct a way that Alice and Bob can signal. So this is what we are thinking of when we think of how Alice and Bob might be able to signal in principle. So let's do it. Let's set up a protocol whereby if we've got violation of measurement independence in the sense of robust dependence of the hidden variables on the settings, Alice and Bob can in fact signal. So, well, it's going to be a sort of standard EPR Bell setup. Charlie prepares an ensemble of qubit pairs in a maximum entangled state. Alice and Bob are doing their spin measurements, except for one thing. Charlie also decomposes the ensemble into two sub-ensembles. And sends these sub-ensembles to Alice and Bob. So for each pair of particles, that pair of particle is either in sub-ensemble 1 or sub-ensemble 2, and Charlie tells Alice and Bob when they send the particle pair, oh, this is part of sub-ensemble 1, this is part of sub-ensemble 2. Now, in quantum mechanics, of course, that doesn't tell them anything. Quantum ensembles. This is a pure state, so it's a homogeneous ensemble. Any decomposition into sub-ensembles, the two sub-ensembles are going to have exactly the same statistics, knowing whether it's the particle pair is from sub-ensemble 1 or 2 makes absolutely no difference. But not so in hidden variable theories. In a hidden variable theory, even a pure state is not a homogeneous ensemble. We can distinguish sub-ensembles in terms of the value of the hidden variables. So in fact, at least mathematically, we can always decompose an ensemble into disequilibrium ensembles. We can at least imagine decomposing this ensemble of particle pairs into two sub-ensembles such that both of them actually violate the Born rule, even though on average if we mix them back together, the Born rule will be satisfied. I'll call that a disequilibrium decomposition. Right. And now we are ready. So let's assume indeed we have a theory that violates measurement independence in the sense that the distributions of hidden variables robustly depend on Alice's and Bob's choices of measurement contexts. And let us also assume that Charlie can reliably prepare disequilibrium decompositions and sends this disequilibrium decomposition to Alice and Bob. In this situation, our first main result establishes conditions under which Alice and Bob can signal. So we need to assume that the hidden variable theory successfully reproduces the correlations of the maximal entangled state. And okay, now the crucial thing is if the marginals of row 1 and therefore row 2 violate the Born rule, then at least one of Alice or Bob can. Yeah. Okay, so theorem 1, what this is saying is, if Charlie can prepare a disequilibrium decomposition, of the singlet state, such that the marginals of either components violate the Born rule, then in this situation, Alice and Bob can signal. Now, let me show you, not in full detail, how I can show this. Let me see. By the way, how are we doing for time? We started at.
We have a little more than 20 minutes.
A little more than 20 minutes. Okay, yeah, all right. So, indeed, not in pitiless detail. So the key ingredient for proving this is theorem by John Barrett, Adrian Kent, and Piranio. Sorry, forgotten first name. Which sometimes is called equiprobability theorem. I'll just call it BKP. Which is, if you want, it's an uncontroversial fragment of the Kolbe-Renner theorem. It's a kind of triviality theorem for hidden variable theories. So we assume that we have parameter independence and measurement independence. And if a hidden variables theory on average reproduces the correlations of a maximal entangled state, then even for each individual hidden variable, it must have the same marginals as the singlet state, as the maximal entangled state. So that means the probabilities for any spin direction are, the probability is 1/2. So in that sense, it's a sort of equiprobability theorem. Now, I'm not going to give you the proof of BKP. This is just a slide for some to convey a flavor of how it's done. So we want to estimate the difference in probability between this spin and this spin, and we sort of interpolate lots of intermediate directions, and we've got two spins in a maximum entangled state, and on this side we've got other directions that sort of sit in between the ones that fill up this chain, and the idea is to estimate the difference in probability between this and this by looking at the correlations between A0 and B0, B0 and A1, A1 and B1, B1 and A2, and so on. And all these correlations, and then we take an average. So for that we need measurement independence, but we take an average, and because these correlations are all given by quantum mechanics, we can give an estimate. We get an estimate that depends on n here, and here we get an estimate of the sort of average of the difference in probability between this and that. And then we let n go to infinity. This becomes 0, and that means that even for each individual hidden variable, this up to a set of measures 0, the difference must be 0, and we get equiprobability. And if we have antipodal directions, then we get that the expectation values of that spin is going to be bounded by something that goes to 0 with growing n. Okay, so that's I'm just flashing this up because we'll need this. We'll need this later. We've got essentially the proof is works by giving an estimate, and we've got a finite estimate, and then we can let, if we wish to, we can let n go to 0, and then we get the exact statement of the theorem as given here. But now, here is the proof of our theorem 1, and this is the last proof I'll give you, because it's lovely. Let's construct a new coarse-grained hidden variables theory. This tells us simply, whether a system or system pair is in subensemble row 1 or subensemble row 2. So we've got more information than in quantum mechanics. If this is a disequilibrium distribution, so this is a non-trivial hidden variable theory, but it's much more coarse-grained than the one we started with. Now, Alice and Bob know whether a particle pair is in subensemble 1 or subensemble 2. Charlie tells them. So they know the values of these hidden variables. So they're subquantum demons for this coarse-grained hidden variables theory. So if we assume no signaling, the new theory must satisfy parameter independence. Otherwise, quantum demons could use that violation of parameter independence to signal. Our coarse-grained hidden variable theory must also satisfy measurement independence, because the distribution, the probability of having mu equals 1 or mu equals 2 is just alpha and 1 minus alpha, and that's something that Charlie controls. And if Charlie didn't control that, if that depended on what Alice and Bob do, then they would also be able to signal, and they would just need to check the size of the respective subensembles, and then they would know what the other has done. So this little new coarse-grained hidden variables theory satisfies both parameter independence and measurement independence. So we can apply the BKP theorem, So row 1 and row 2 have the same Born rule marginals as the entire ensemble. So assuming signaling, indeed, the marginals must be flat, and that's the contraposit of theorem 1. Again, I'll just flash the statement of theorem 1 for you in case I'm going too quickly. Right. Now I'll go quickly, however, because I just want to say, if we don't take the limit of n to infinity in the proof of BKP, then we can get another theorem I call it BKP prime, in which we are weakening both the assumptions and the conclusion. It's got the same flavor, but both assumptions and conclusions are a bit weaker. So we don't need to reproduce on average all the correlations. Only certain correlations, the ones that we are actually going to use in the proof. So we haven't let n go to infinity. We're only using finitely many correlations. But then, our estimate is not going to be as good. Then the marginals, can deviate, from the quantum mechanical ones at most by a finite amount. And if we use this BKP prime theorem instead of the BKP theorem, we can prove a variant of our theorem. Again, we don't require the hidden variables theory to reproduce all the correlations, only a finite set of correlations, and then we need a stronger condition for Alice and Bob to be able to signal. Then the marginals of this disequilibrium distribution need to violate the Born rule by a finite amount, and then Alice and Bob will be able to signal. Okay. So indeed, so what we've seen here is we've got some conditions under which signaling in a zigzag is possible in principle. We've got this protocol where Charlie having to reliably prepare disequilibrium decomposition. We've got robust dependence on Alice's and Bob's settings. But if these marginals violate the Born rule or violate the Born rule by a certain amount, then Alice and Bob can signal. Now, marginals violating the Born rule, and that sounds a bit abstract. Can we get a handle on when such conditions might be satisfied? Yes. And let's do it now. We're really interested in the kind of implications, or in the implications of violations of the Bell inequalities. So let's go back to Bell's theorem and see if one can derive the Bell inequalities, even relaxing the assumption of measurement independence. And we are not the first ones to do that. People have been doing that, by sort of quantifying and sort of restricting the amount of correlations between the hidden variables and the settings. We do it differently. We restrict how much the hidden variable distributions may deviate from the Born rule. I won't give you the proof of this because it's uninteresting. But we can indeed, derive the Bell inequalities even if measurement independence is violated, or rather, now we are considering a theory in which both outcome independence and parameter independence are satisfied, but measurement independence is violated, and okay, if disequilibrium decompositions satisfy a certain technical condition, and this is these expectation values must be small, so they can't. And in the case of the Born rule, they are 0. So this is a restriction on how much the hidden variables theory can deviate from the predictions of quantum mechanics. If the deviation is small enough, then even though we are violating measurement independence, the Bell inequalities follow. And so, in order for the Bell inequalities to be violated, there must be a disequilibrium decomposition and a pair of observables A and B, where such that this condition is satisfied, and well, not by coincidence, this has the same form as the condition that we used in theorem 1 prime, when we were looking at finite number of correlations and so on, and it's motivated by its coming up in our previous theorem. So now we've used the same kind of condition to be able to derive the Bell inequalities. So if we violate the Bell inequalities, we'll have that, and then we can apply theorem 1 prime, and we get signaling. So putting everything together, our final theorem is if we have a theory that violates just measurement independence, and if it violates the Bell inequalities, but reproduces certain a finite number of other correlations as well between different spins, then if Charlie can reliably prepare the disequilibrium distribution that we've just seen must exist by theorem 2, if the theory violates the Bell inequalities, then it must these marginals must violate the Born rule by a certain amount. So if Charlie can reliably prepare that disequilibrium distribution, then at least one of Alice or Bob can signal. So it's just putting together the two results. Right. Now that's all the technical stuff, and all that we need to do now is draw conclusions from this. And how much time have I got, Jacob?
You have about 7 or 8 minutes.
Okay, good. Thank you. Now, many of you will have heard the lovely phrase experimental metaphysics, coined by Abner Shimony. By that he meant that experimental violations of the Bell inequalities tell us that there's some form of non-locality in the world, whether or not quantum mechanics, irrespective of whether we believe quantum mechanics to be empirically correct, there's some form of non-locality in the world. That's what the experimental violations of the Bell inequalities tell us. But what kind of non-locality it is, violations of outcome dependence, parameter independence, and so whether this form of non-locality is in fact compatible with relativity or not, depends on indeed on the details of which condition that is violated. So that's Shimony's experimental metaphysics. What we want to propose is that we can extend this program of experimental metaphysics. Experiment tells us the Bell inequalities are violated. The maths tells us that in order to violate the Bell inequalities, we have to violate outcome independence or parameter independence or measurement independence. And now what's new is we can draw some metaphysical conclusions similar to the ones that Abner drew, but also from violations of measurement independence. And specifically, we get a new way, a new kind of non-locality, if you'd like to call it, stretching a bit the meaning of non-locality, one that is compatible with relativity, because that's a motivation for looking at violations of measurement independence in the first place. We have compatibility with relativity, but we have signaling in principle. Now, this is something that was not covered yet by the various options that were envisaged so far. Now, what's the argument? So, experimental violations of the Bell inequalities have ruled out, essentially, also the conspiracy loophole. So, if we have violation of measurement independence, it's not of the sort of common cause type. So it's going to be of the interesting type. Now, of course, we can also rule out that the hidden variables influence the settings. So it's going to be of the interesting type. Settings influence the hidden variables, or we have global constraints. But in either case, there's a robust dependence. If the settings are different, so is the distribution of hidden variables. So we can, in fact, apply our result, or rather, assuming that any experimentally viable theory, because any experimentally viable theory must reproduce the Bell inequality violations and reproduce these few extra correlations that we are talking about in theorem 3. The premises of our theorem 3 are experimentally warranted, so we can conclude that in any case in which we may have outcome independence and parameter independence, there will be signaling in principle if Charlie is able to reliably prepare disequilibrium decompositions of this form. That's the conclusion. Now, experimental metaphysics has to be taken with a pinch of salt. There are one has to be very careful about exactly. If we've got cases in which we have both violation of outcome independence and parameter independence, then it's not very clear cut. What we should think. And violation of outcome independence on one level, might in fact be explained by violation of parameter independence at some deeper level. The standard quantum mechanics violates outcome dependence. The Bohm theory violates parameter dependence. So what looks like a violation of outcome independence might in fact be violation of parameter independence at a deeper level. One has to keep in mind all these subtleties. And that's going to be the case also in our analysis. But we have to be especially careful because we have this this condition that Charlie should be able to reliably prepare. Sorry, this should be disequilibrium decompositions, and that turns out to be sort of trickier than one thinks. And I'll just say why, and that's going to be it. And we can keep this slide for the Q&A if you want to know about, if you're interested in stochastic electrodynamics, stochastic mechanics, ask me a question and I'll come back to this slide. Okay, should Charlie be able to prepare these disequilibrium decompositions if such a theory is true? Now, it's not obvious, because if Charlie starts with a quantum ensemble, how are they going to sort of decompose it? So, they would have to know the hidden variables to start with. They would have to be subquantum demons. That decomposing an ensemble won't work. But if Charlie has some reliable sources of disequilibrium, Charlie will be able to sort of mix different disequilibrium ensembles to yield an equilibrium ensemble. So that seems to be the way ahead. It is pleasingly similar to what you have to assume in the case of pilot wave theory. The possibility of reliable sources of disequilibrium, and that seems to be clear enough. I mean, contentious for some. Seems to be clear enough in the case of the pilot wave theory. We have a detailed dynamics that tells us how distributions evolve in time, might relax to equilibrium, and so on and so forth. We've got an understanding of how that works there. And we need that kind of thing also, for theories violating measurement independence. But that doesn't always happen. Here's a toy example. Our theory violating measurement independence is such that the hidden variables are just values of spin in the directions that we are going to measure, distributed according to the usual quantum mechanical distribution. That's clearly a theory that reproduces all the predictions in the Bell case, violating measurement independence. But there is no mechanism for enabling anyone to prepare disequilibrium distributions. So this is a toy example, or it looks like a toy example, but it isn't just a toy example. Here are two ways of implementing this. If you have a theory, a collapse theory to collapse along the past light cone, the kind of thing that Helvig and Krauss proposed in the 70s, or if you take the Everett theory and with a sort of non-standard branching along the past light cone, the only difference between the two is that in the collapse case we've got ors, a certain state or another state, and in the Everett theory with branching along the past light cone, it's and. They're both, they're all realized in different worlds. And maybe think of collapse along the past light cone if that's easier. I mean that is our toy example. In the past light cone of, say, Alice's measurement, the state has already been collapsed by Bob, and vice versa. So it's already, a state that has been collapsed, and it's going to produce a certain result. And the fact is that there really is no way. And we know that in this case, because we know fully what's happening. There is no way that Charlie could ever produce a disequilibrium distribution. Disequilibrium distributions in a collapse theory are only statistical flukes. And if you're thinking about Everett with past light cone branching, disequilibrium distributions correspond to deviant worlds. That's not under Charlie's control. Whether you live in whether they live in a deviant world or not. So and maybe there are other examples where, in fact, it's not possible in principle to prepare these disequilibrium decompositions. But at least in these examples, I think what's happening is that really it's totally underdetermined, really. I mean, collapse along the past light cone or collapse along the forward light cone. There's no experiment that's ever going to distinguish between the two, or how you think of branching, how branching fits with the space-time notions. I think it's again a sort of conventional thing. I mean, the universal wave function is what it is. The way we think that we can subdivide it in branches, at space-like separation and so on. Those are just sort of convenient ways of thinking. So as far as I can see, these funny examples come only from cases where there is this sort of radical underdetermination or sort of conventionality, and so it's really ambiguous whether we have violations of measurement independence or violations of outcome independence. And if that's the case, then indeed, maybe in all unambiguous cases where we have mechanisms where measurement independence is violated, we have indeed shown that we can think of that as a third possibility of some kind of non-locality compatible with relativity, but where we have signaling in a zigzag, thus completing the Abner-Shimony's program of experimental metaphysics. And that's all I wanted to say.
All right, so we're back for the discussion and Q&A. The first hand I have is from Wayne. Wayne, hello.
Hello, how are you?
Doing well.
Good. What if someone asked an inappropriate question during the live session? You had this distinction between appropriate and inappropriate questions in the chat.
I just meant a question that would be lengthy or require an extended discussion should be said. Anything that required a quick technical point that you could ask during the.
Okay, I'm pretty sure my question's an appropriate one. Guido, this is really interesting stuff. I want to ask you to say more about the role of these sub-ensembles and the assumption that Charlie can prepare these non-equilibrium sub-ensembles. In connection with things like, so among the people that are advocating violations of measurement independence these days are Tim Palmer and Sabina Hossenfelder with a sort of super determinism thing, which I think counts as global constraints in your taxonomy. So what what relevance, if any, does this result have to them? 'Cause I mean, I'm kind of guessing that they would say that if there's global constraints about the measurements that Alice and Bob make, there's also global constraints about what preparations Charlie can do. So, any thoughts about that?
Well, I'm not convinced that those constraints would rule out these equilibrium decompositions. I mean, might be that they yeah. I mean, it may depend on the details of the theory, but I don't know. I mean, suppose that in fact we have a deterministic theory, and well, I mean, the constraints would have to be so strong that there's a unique distribution of the hidden variables, of all the variables that's possible. Now that's usually not the case in even in a deterministic theory. We can always have some ignorance over what the exact values are. So we can always have a probability distribution, and this probability distribution will then evolve according to the deterministic laws. But it's usually not unique. Mm-hmm. So if something in the theory makes the possible probability distributions unique, it must be something really pretty strong. They may have something like that in mind, but it would be non-trivial, I think.
Thank you. That's a good answer. I'd have to look more carefully. I suspect that they actually do and want to have something that strong that determines unique probability distributions. But again, what matters is the details of the theory, as you say.
Yeah.
Great. Thanks. Next question I have is from Lev. Lev, go ahead.
Thank you, Guido.
Pleasure.
I'm after a 12-hour flight, so I'm not sure I'm fully grasps the whole talk, but there is one thing which is very close to me, and this is I want you to clarify. I'm struggling with David Deutsch, David Wallace, who are trying to say that the words, average words, spread out with velocity of light, and I cannot make any sense out of it. And now you introduce a new thing that this average word happening on a past light cone. So if you can clarify what do you mean by all this. And another related question, it's not clear for me what Everett does with Bell inequalities. For me, there's no any Bell inequalities for Everett. Every time you perform quantum measurement, all outcomes happening, and Bell relies on particular outcomes. So there is no how you defined the Bell inequalities in Everett framework.
Yeah. Okay. So actually, let me maybe go to sort of simpler setting. So let's not think about space-time and light cones and so on. Just sort of non-relativistic Everett theory, and I mean there are sort of a number of authors and I mean, maybe you are not particularly interested in that kind of debate, but it's something that David Wallace, Simon Saunders have engaged with. The idea whether we should think of branching as splitting, here we have, for instance, a measurement. Until then we have, one world, and then we have two worlds, for instance, or whether we should think of it as worlds that diverge. We had two worlds even before that measurement, but they were indiscernible. Until this measurement, they look exactly alike, and after this measurement, they look different. Now, the way I think of that is, this is not a substantial, difference. What's out there is the universal wave function, and what's also physically physically interesting is that after the measurement, we are going to be able to distinguish two different components, which for instance, don't interfere with each other anymore, etc., etc. But that's what the physics tells us. Universal wave function, and after the measurement, two different components. Whether we think of branches as being one branch before the measurement or two branches before the measurement, I think is just a choice of description which doesn't correspond to anything in the physics. It may be more convenient to think in terms of divergence if we want to think of probabilities in terms of ignorance, rather than in terms of a caring measure or something like that. But it's up to us to choose that description, as we see fit. I think it's the same in the case of relativistic Everett theory. Again, there's going to be one universal wave function, and the physics includes also if we have a measurement, it includes also, say, formation of records along the forward light cone of that measurement, and that's in the physics, and we have formation of records for Alice, for Bob, that's all in the physics. But branching, that's again a matter of sort of convenient description. Should we think that Alice's measurement is associated with branching also on Bob's side and vice versa, or should we think of Alice's measurement as associated with distinguishing two branches only in the future light cone of her measurement? I think that's just a choice of description that we might make for purposes of convenience. Branching along the past light cone would be another example. It's a stranger choice, but not much more weird than thinking of branching happening at space-like separation. So that's what I think about these different descriptions of branching. That was your first question, or the first part of your question. Remind me of the second part of your question.
The second part, you put this in the context of Bell inequalities.
Yes. Everett and Bell. What have they got to do with each other? Well, in each Everett world, we see that the Bell inequalities are violated. So, of course, if we say, I mean, there's, we can say, look, Bell's analysis does not apply because one very, very, very basic assumption of Bell's analysis is that we have single outcomes. So that is violated in Everett, so we don't need to worry. But in an individual world, we do have an individual outcome. I mean, there are many things that, from the point of view of the universal wave function, are not there, which are there in individual worlds. There's determinism at the level of the universal wave function, and there's indeterminism if we are looking at what happens inside a world. So one thing that happens inside a world is also that the Bell inequalities are violated. So if we look at well, and then if the Bell inequalities are violated in a world, it means that one of the assumptions of the derivation of the Bell inequalities must be violated in that world. And while clearly under no description of Everett, presumably, we're going to have, well, who knows? I mean, in some deviant worlds look like the Bohm theory. So, maybe in some deviant worlds, explanation looks like violation of parameter independence. But I think there is, I think the most natural or most obvious description of what's happening in single worlds is violation of outcome independence. We have just these mysterious correlations, between, I mean, from the point of a single world, we just have correlations between Alice's and Bob's outcomes, and they become unmysterious if you look from the point of view of the universal wave function. But inside a world, formally, we have violation of outcome independence. That's a natural way of thinking, but depending on how you think of branching, another way of thinking might be what's happening is violation of measurement independence. If one thinks of branching as along the past light cone, maybe it's not a very natural way of thinking, but if one thinks of that along the branching along the past light cone, then the diagnose of how in a single world the Bell inequalities are violated will be in terms of violation of measurement independence.
May I just briefly comment on the second part, how I view it? I think the whole idea of many worlds is that when we perform measurements, all outcomes happening. And we cannot ask what is the probability for particular outcome. This question is just illegitimate. The world, we cannot look what will happen with my world in the future. My world in the future will be many worlds. So the only way to look is backward in time. Backward in time, there is a single world, but then there was a particular measurement in Bell inequalities, and we have no problem. And to the future, we cannot talk about it because we are not allowed. We cannot ask what will be in my world in the future. There will be many worlds, so this is not one outcome. So, but there are many other people. I don't want to.
Yes, and if you talk to David Wallace, or Simon Saunders, they will think of probabilities towards the future, and then I guess the question of violations of the Dale inequalities will be relevant for them.
Thank you.
Pleasure.
I have a follow-up to that, actually. So looking backward, right? So, in practice, to do a Bell experiment, you have to prepare a large number of pairs of particles. You have to generate a large number of measurement statistics if we're doing the standard Bell setup. And then looking back, right, when you compute the statistics, looking back, don't you expect to see the measurement statistics in general to violate the Bell inequality? I mean, even in a many worlds context, sure, you have one branch when you look backward, but wouldn't the measurement statistics in that branch show a violation of the Bell inequality?
I take it this is a question to Liv.
Well, I guess it's to both of you. It's to both of you. Because you're both trying to make sense of what it means to talk about Bell inequality.
In a single word, we see backward in time. The statistics as our world. In every hour world, we perform this experiment at many Nobel Prize and all other experiments. So of course we see the statistics.
Yeah.
But we cannot define any kind of. We cannot ask what would be if we did perform as a measurement, because in every case it was only one particular setup. So when they're all different, we cannot mix them together. It will not.
Sure, but is it still fair to say that, right, the Bell inequality is stating an empirical thing that you could go out and you could in a many worlds context, you could run the Bell experiment, you could look back at all the statistics of the experiment, you could see a violation of the Bell inequality, and that's a robust prediction of quantum mechanics. And at least in that sense, it makes sense to talk about the Bell inequality, even in a many worlds context. That is it okay to talk about the Bell inequality in that way in a many worlds context? I think so.
But we have to add that this is illusion.
Sure, that's fine, but at least it's a robust empirical prediction.
Yes.
Good. All right, thank you very much for clarifying. That's very helpful for me too. And Guido, does that you're okay with that too?
Yeah, I mean, I guess in the statistics, there will be these correlations. There will be violation of outcome independence. In the statistics. But in an Everett setting or Everett looking backwards, we don't worry about that.
All right, thank you very much. The next hand I have is from Kent.
Thank you. Can you hear me okay? Good.
Yes.
What I hope is a simple question. One of the things that, of course, worries people a lot about superluminal signaling or tachyons or anything of that nature is the risk of setting up closed causal loops, which can lead to interesting paradoxes. So, for example, if Bob can signal superluminally to Alice, and then she can reply, hitting Bob's world line at an earlier point, she can blow up his laboratory or something before he sends a signal. And so now you seem to be, if I understand correctly, you're arguing for some at least limited degree of superluminal signaling in this kind of zigzag retrocausal picture. Is there a simple question? Is there any danger of closed causal loops in this picture?
Well, yeah, I mean, I wouldn't call it superluminal, precisely because it's zigzag, so it's going to be subluminal this way and then subluminal that way. But it is a signal from here to there, between points that events that are at space-like separation, danger of sort of causal paradoxes. I think it's this sort of standard situation. We are allowing for retrocausation, so there are going to be causal loops possible, but causal we want them only to be sort of consistent causal loops. Inconsistent causal loops will be impossible, and but the question is, okay, you know, should we worry about theories, you know, that allow for causal loops for the usual reasons of you know, possible, I mean, causal paradoxes. You know, what prevents the causal paradoxes, and well, I personally you know, hold the sort of relaxed view that well, you know, any solution to the laws of physics will have to be consistent, and you know, if the laws of physics allow for you know, causal loops, they'll have to be consistent, and you know, if that messes about a bit with our intuitions, well, so much the worse for our intuitions. You know, we must find a way to stop worrying. You know, but yeah. So that's the way I think of it. I don't think there's anything new with respect to, you know, the grandfather paradox in anything I've been saying.
Okay, thanks.
Thanks, Kent. The next hand I have is from Gerardo. Please go ahead.
Hi, can you hear me now?
Yes.
Oh, nice. Hello, everyone. Thank you for the talk. It was very interesting. I have a few questions, but I will limit myself to just one for the moment, okay? If I understood correctly, one of your claims is that a theory in which you deny setting, you call it measurement independence. Sorry, I used another term.
Yeah, no worries.
Will respect relativity, but will violate signaling, correct? Or at least it is possible to have such a theory, right?
Yes.
Okay. How are you understanding adherence with relativity here? Because the thing is that, at least for some authors that have been very important in the literature, I'm thinking of John Jarrett. He used to identify adherence with relativity precisely with no signal, right? Mm-hmm. So the idea was that if you violate parameter independence, you will get signaling, and that's why you will violate relativity. So what exactly are you using or understanding adherence with relativity here?
Yeah. So the signaling, you know, that appears here is not space-like. It's not superluminal. So what's I mean, I guess one way of seeing it is it's not signaling that can be used to you know, introduce you know, a preferred frame or preferred foliation. You know, in the Bohm theory, we have, you know, superluminal signaling. You know, there is one frame in which you know, the action at a distance happens, and you know, in any other frame, the theory looks different. And yeah, in principle, you know, we could use, you know, if we could signal, if we had disequilibrium distributions in the Bohm theory, we could signal at space-like separation and use that to, you know, synchronize clocks, you know, introduce absolute simultaneity, and you know, that would be incompatible with relativity. If we've got you know, signaling in a zigzag, then there's no way yeah, so the signal goes backwards and then goes forwards, and I know, but okay, I mean, how far forwards do we need to go in order to introduce a sort of clock synchrony? I'm not sure there's any way that that we can actually use that to really do. I mean, yeah, I mean, one has to think carefully about what relativity prohibits, but yeah, I don't think you could use this. You can use this kind of signaling to, for instance, introduce a preferred frame, or introduce a sort of absolute notion of simultaneity. Yeah, of course. I mean, it's one should think all these ideas through, because it's unusual to, yeah. But if you've got special relativity and you allow influences backwards in time. I mean, if you take electrodynamics and allow both retarded and advanced solutions, presumably there's no way of introducing a preferred synchrony convention, and so on and so forth. And I think
see.
It's the same. Yeah,
I see, but I don't understand why you have to put it in the sense that you need a preferred foliation. Perhaps you don't need a preferred foliation to have signaling, right?
No. In fact, here, we're saying you can have signaling, but without preferred foliation. So it's a different kind of signaling. So it's a it's a more benign kind of signaling. A signaling without preferred foliation. And yeah.
Well, I mean, special relativity is in principle a part of general relativity, and in general relativity, in a generic space-time, there's no preferred foliation, but you can certainly, in principle, have closed time-like curves and wormhole geometries in which signals can get from one point in space-time to a point that in some sense is space-like separated. It's a bit ill-defined whether it's space-like separated if your space-time itself has a non-trivial geometry.
Yeah.
But at no point are any signals moving along space-like trajectories. They're only moving along time-like and null trajectories. In a sense, sending signals along time-like trajectories, but then they reach points that are space-like separated is a bit like a wormhole type thing. And I don't think anyone has proposed that CTC, closed time-like curves, or wormholes are at least prima facie violations of relativity, given that they are, formally speaking, at least potential geometries that space-time could have, right? Does that comport kind of, Guido, with like, yeah. So the kind of signaling we're getting here is of the kind that one conceptually one might imagine in a non-trivial space-time geometry.
Yeah.
Gerard, does that sound okay though? I mean,
yeah, I think. Yeah.
Thanks, Jake.
Okay. I know, Gerardo, you have more questions, but it looks like Wayne has a question. And because Wayne went first, Wayne, you go, and then Gerardo, you can come back and ask more questions. Yeah, I have questions too, by the way. I don't ever raise my hand, but I always have questions. Wayne, go ahead. Mine is actually a comment on this previous discussion. So I'm just going to say it, and then we can go back to Gerardo or you. One thing, like this question of compatibility with relativity, one thing I found very helpful to distinguish in my own work is between two very different things that people might need.
One is respecting the invariances of Minkowski spacetime, right? So that would mean not introducing a preferred foliation. And then in general relativistic context, that would be doing it locally and approximately, right? But the other thing that someone might mean, and I think is actually the more interesting thing, is typically people associate with relativity a certain causal structure, meaning that meaning that causes of an event are confined to the past light cone. And that the notion that special relativity requires that comes explicitly, and Einstein was the first one to say this in 1907, from the idea that, okay, the past light cone are the points that every reference frame agrees are temporally in the past, and the idea that causation is a temporally asymmetric notion, that the cause of something is in the past. So I think that we should distinguish those two, because if you're going to have these zigzag correlations, you are violating what I just called relativistic causal structure. You're not saying that the causes of things are in the past light cone, but you're doing it in a way that respects the symmetry of Minkowski spacetime. So I mean, I think that that's a useful distinction. I think there's two very different kinds of concerns that one might have about compatibility with relativity. If you don't think that causes have to be in the past, or that a signal has to be sent before it's received, then there's no particular reason to think special relativity forbids superluminal signaling or superluminal causation.
Yeah, this is why I introduced the general relativity example, right? Because if you're doing quantum mechanics on Minkowski spacetime and special relativity, then you are violating that proviso, Wayne, that you just said, right? You're having causal influences that go backward into the past. But in general relativity, if you have a sufficiently non-trivial spacetime geometry, right, then if you have wormholes or closed time-like curves, well, then signals getting from one point in spacetime to another point that might naively look like it's arriving someplace outside your past light cone is actually not arriving outside your future light cone. Is actually not outside your future light cone at all. The non-trivial causal structure makes points that might have seemed, there's a point in the Andromeda galaxy that you might naively think is space-like separated from you, but is in fact not.
Yeah, so here's what I want to say about that is, like, so in Minkowski spacetime or any global hyperbolic spacetime, I can say, okay, here's this causal relation, relation of causal connectability, that the cause of an event has to be in the past light cone, right? And that's because you're in a spacetime in which, given any point, the light cones are in two disjoint sets, past and future, right? Now, if you've got closed time-like curves, it might be that you don't have that two disjoint lobes of the light cone, right? It might be that you can go ahead in the future and end up in the past light cone or something like that. In which case, if you try to apply that criterion of causal connectability, is actually a trivial relation. Every point, it might be that every point is causally connectable to another.
Good. So I mean, ultimately, it all sort of hinges, just like you said, on exactly what you take to mean a violation of relativity. And at the very least, violating relativity in a new way is interesting. Great. All right, Gerardo, you want to continue? I think you have more questions.
Actually, if I
please.
Sort of add to that, I mean, the idea, I mean, cause-effect relation is asymmetric, but even independently of relativity, then the prize question, is okay. I mean, should that asymmetry coincide with the past-future asymmetry, or are these two independent asymmetries? And if we translate that question to the relativistic setting, that just becomes okay. If they coincide, we have sort of relativistic causality in the sense that when just introduced. If they don't coincide, then what relativity is adding is that causes and effects need to be at least locally related in a time-like way, but there's no requirement that the cause be in the past of the effect, and that's a sort of different way of I mean that would be then the way to argue that for compatibility with relativity, but insisting on the fact that the causes need not temporally precede their effects.
Can I just ask a quick clarification? Sorry, I don't mean to jump the queue or Guido, you said that that special, even if you give up the idea that the causes have to precede the causes, special relativity says they have to be related in a time-like way. Why?
Mm-hmm.
They don't have to be related in that time-like way with the cause to the past of the effect. Why should I think they have to be related in a time-like way?
Well, I mean that seems, I don't well, I mean, if you take well, if you sorry that I don't know. Sorry, it seems somehow obvious to me, but that makes it difficult to explain. I've sort of always thought of causal structure in special relativity as distinction between time-like and space-like. Light cones. That's what's important, and that's what's new. We've got as a distinction that we didn't have in Newtonian physics, and somehow the idea that physical influences cannot travel faster than light means no physical influences at space-like separation, but physical influences, or causes, if we want to talk, well, if we want to introduce the concept of cause, or if we're talking in terms of functional dependencies, sort of domains of dependence and so on, that all becomes time-like, as opposed to space-like, which is and somehow the direction of time sort of never enters into that kind of reasoning.
I have a couple of follow-ups on this, but I want to make sure that we get Madeline, because we have a new question. So Madeline, why don't you go ahead?
Yeah, and mine actually was a follow-up on this too, so that's helpful. I noticed that there's kind of been discussion of different ways of approaching violations of relativity, with kind of non-intuitive causal structures. So I'm curious, kind of broad sweeps from a metaphysical perspective, what ways are most important for kind of preserving locality? Because I know that you can, in terms of like Bell analysis, you can start venturing into the realm of like parameter independence, where you have like superluminal signaling, and kind of how do you prioritize which things are worth kind of sticking to when developing explanations for this sort of thing?
Yeah, well, I mean, I should think, well, I mean, violation of parameter independence, if it is indeed sort of fundamental. I mean, that extra slide which I skipped, was apparent violation of parameter independence could just be a sort of coarse-grained description of violation of measurement independence. But if we have sort of fundamental violation of parameter independence, that's clearly incompatible with relativity. We don't like that. Violation of outcome independence, that definitely seems to be sort of well, that's weird, but mild. And violations of measurement independence, that allow for sort of zigzag, causal influences. Well, I suppose what we're doing now is wondering whether that's worse than, not as bad as parameter dependence, but worse than outcome dependence, or whether it's just as innocent as outcome dependence, or even better than outcome dependence, because now we can violate the Bell inequalities using purely local mechanisms. I think proponent, somebody like Hugh Price, I think would say that's even better, even more more benign, than violation of outcome dependence, because now we just have sort of usual. I mean, we can explain the distant correlations, through local mechanisms. So we have so in that sense, even though we may have signaling, it's even more benign than violations of outcome independence, which don't have signaling. But I guess one can disagree. Maybe the fact that we do get signaling, even if all processes are completely local, is should be seen as a comparative disadvantage with respect to outcome dependence, where no signaling is possible at all. Depends what you like, depends what you dislike, and I guess it's only once we start putting these options on the table that we can really think through which options we prefer and for what reasons.
Okay, that makes sense. Yeah, I guess it depends on how you define like benign in a metaphysical sense. Yeah. Thank you.
So there's a bit of a subjective aspect to this about which preferred way you have, which one you want to give up. Now, of course, some of these conditions, and I'm thinking outcome independence in particular, may also depend on other background facts, other background assumptions, right? Outcome independence is closely connected with like Reichenbach common cause principle, right? That like if you don't assume the common cause principle, it's not obvious that outcome independence should hold even separately from the question about relativistic consideration. So I think more comes into this, right? There are more, because some of these conditions, Madeline, depend on other background philosophical, metaphysical assumptions, you also have at your disposal whether you would prefer to get rid of some of those, right? I mean, Guido, would you agree?
Yeah, sure.
That makes sense, kind of getting the full picture of what exactly you're adopting as your understanding.
Great. All right, thanks a lot. Then
Can
we're going
I
to go back to Gerardo. We have about 5 minutes left, and then we're going
Yes,
to finish on the hour.
I will
Go
try
ahead,
to
Gerardo.
be really fast.
It's okay, good. We're okay with time. Go ahead.
Okay, so the question was going to be why it is not trivial to say that if you have violations of measurement independence, you have signaling. Okay, but let me try to connect it quickly with our previous discussion. The thing is the following. So when one considers a retrocausal theory, one imagines that what is happening and what one desires is to extend something to our physical theories that respects as much as we can of relativity as possible. Okay, so in relativity we have this idea that, well, the causes of an event can only be in the past light cone, and we will extend it and we will say that now the causes of an event can be in the past light cone and in the future, and we want to restrict interactions along light cones, and that looks really nice until you think that you realize that this kind of story will allow you to connect any point in your space-time with any other point. And when you say that, you notice that you lose a little bit the distinction between points that are space-like and time-like separated, and that is pretty bad, I think. And that's why I think that it's really, really important to answer in what sense a retrocausal theory respects relativity. Okay, so perhaps.
I had this is very related closely to the question I was going to ask, right? That in a way you're getting between space-like separated events indirectly, like by doing a bank shot, with your, instead of connecting directly between the two events, you're connecting with a pair of time-like world lines. I completely agree. That's an interesting question. Guido, what are your thoughts?
Yeah. Well, is this different from your earlier question?
Perhaps we can go to
are you just expressing shock?
Perhaps the quick one, the why it is not trivial to say that in a theory where you allow causal zigzags.
Okay, yeah, yes, yeah, that's new. Well, in the Bohm theory, we have action at a distance. Now, why isn't it trivial to say in the Bohm theory that you have signaling? It's not trivial, because signaling can be masked by sort of statistical effects. On each individual run of the experiment, Alice's choice does determine what the trajectory is, but on average, it doesn't. In equilibrium, it doesn't affect the probability of Bob's result. So it's not trivial, even in the Bohm theory, to point out how you can get signaling, even though there's action at a distance. And I think it's the same at the statistical level. There is no zigzag signaling under normal circumstances. We have to find the specific circumstances in which that will become visible. And that's a technical work that we do in the paper.
We're going to have to leave it there. Thank you very much, Guido. That was an amazing talk, and thanks for leading an amazing discussion in Q&A. It's
Thank
nice
you.
to see everybody
Right.
here. Thank you all for spending the last 2 hours with us. It's really great to see you all and be back for the fall term. We have talks every 2 weeks. And go to the website and you can see all of our previous talks. There's a YouTube channel with all of the recordings of all the talks we've had so far. I was saying before that we've hit over 2,000 subscribers, and who would have thought that there'd be more than 2,000 people who want to see videos on talks on foundations of philosophy of physics, but that's great. And obviously, any of you are welcome to reach out to me at any time. I'd love to hear from all of you. I hope you're all doing well and have had a good summer. So stay tuned. There'll be an announcement for the next talk that will be coming up soon, and the next talk will be in 2 weeks. Thanks again, Guido.
Thank you. Thanks, everyone.